Here is I'm making additional unnecessary things. Only 2 cells, sorry. And here the radius to the midline 5 to 25, and from here to midline is 30, and the unit is in millimeters. So for this material, we are given E equal to 70 GPa and mu equal to 0.033. So therefore, from here we can calculate G.
Is that a symmetric object?
Yeah, this is symmetric.
So that middle beam is not really necessary.
Yes. Okay. So from here, we are given the torque equal to 22.5 kilonewton meters. So we can calculate the angle of the twist, and then we're going to calculate the shear stress in each walls here. And for this case, we can calculate the first one. You can see the shear flow again. Because this is symmetric, and the shear flow, the Q1 and this is Q2. And here I do the shear flow that should be going inside here, and you can see the middle part here. Basically, this wall, the shear flow canceled from each other. Okay, so basically here, if you want to try to reinforce this design by simply adding a wall in the middle, basically you do nothing. Okay, because then there's no shear being going to here, so basically this is redundant. Okay, so that means this one basically equivalent is we could imagine there's no such things here. So the whole thing will be equivalent to is just the things like this. Okay? Okay, so for this case, you can calculate the A. The A will be the area for the whole things. Okay, for the whole thing. So this one can be calculated is 60 by 50 and plus 2 times pi over 2, the up and down, the radius, the circular area. So this one is 4.963 times 10 to the 6 millimeter square. So therefore, we can calculate tau. Tau equal to T divided by QAT. And what is the thickness? The thickness is uniform. millimeters. So this one, although it looks like it's a multi-cell section, but actually it's a single cell section. So this one we plug in everything, and then that will be equal to 50.4 MPa. Okay, this one only exists in the circumferential walls. Okay, so then you should be able to calculate the angle of the twist per length. So again, this one by definition is the angle of the twist per length, and here the length is protruded from the wall So here it depends on how much length you want to do it, but here we just simply take the unit. And this one basically equal to T and 4G A squared, and for the circulation ds divided by T. So this one pretty much straightforward because T is the same everywhere through the whole circulation. So here this basically is T divided by 4G and A. So this one basically is equal to the whole length of the circulations and divided by thickness. So let me get the thickness out here. So here we simply work on the length, the circumferential length, and that is equal to 4 times 30, and that on the 2 sides, and then plus the circular path is 2 pi times 25. Okay, and this is in millimeter. So, and we plug in everything. So G here for the calculation is 26.32 GPa. So we plug in everything here. That will give us is 0.0534 radian per length per meter. Okay. So for the design, if you really want to take advantage of the additional support through, then you better not to place that one at the middle. You can go up a little bit or go down. Okay, so that could be your other classes or your senior design things. This one, this concept won't be seen in traditional mechanics material because we don't have that the foundation to justify this, but now you do have.
So the only time we'll ever have to do an integral from ds over t is if you give us like some type of linear, like a function or something, right?
Yes, yeah, if the t will be, for example, in terms of the test or exercise, then to implement this one, I do need to, I think I need to give you very precise information. Yeah, otherwise this one have to go to the numerical finite difference, piece by piece, piecewise adding. Okay, yeah. But everything in engineering, you do approximation. That should do the work. Okay, so now how many we have done so far, and I kind of give you a summaries. We have done